able to give you an overview today on an idea that the European Business Council is supporting from a small German company called TechnoCarbon, how a lot of CO2 can be removed from there by enhanced rock weathering in making building materials. The building materials are made from stone, and the same stone we are using is able to capture CO2 if it is grinded into flour. And in cutting the stone we are using, a lot of flour will be derived as a byproduct of this cutting process. To make it very simple for you in the beginning to understand what we do, we make building materials from the same stone that we use for weathering of rock. And it's a circumstance that is really fortunate because the same stone can do both things. The stone we analyzed is best suitable for building materials due to its consistent structure, and it also stores even more CO2 per kilogram than basalt. While basalt is a little bit more fragile, it can be used for certain applications too, for the buildings side. But in this case, we found the ideal stone to do both. Next slide. So the problem we are facing today is building materials from cement and steel. So cement alone is about 8% of all global emissions, with 3 gigatons per year. We will be more people on the planet that want housing until 2050, so increasing cement demand will happen. And all the current investigations and efforts to make cement greener are more or less not scalable. They hit limits, scalability limits very fast. So without a breakthrough in the building sector, that's our belief, a 2-degree target will fail simply due to cement failing to be really decarbonized. And steel is another 3 gigatons per year. So we talk about in total about 6 gigatons CO2 only from steel and cement. That is about 15% of our global emissions. That means if steel and cement would be a country, it would be right after China, the second largest emitter. Next slide. So there are many attempts to decarbonize concrete, and I don't want to go into too much detail here. Concrete claims that they can store in the cement, and all these mechanisms need a lot of pure CO2. And where shall all this pure CO2 come from? There will be CO2 from air capture, but that's by far not enough to be stored in cement, to make these kind of cement scalable. We talk about 4 gigatons of cement that we need every year, so that means that we need CO2 in the order of at least 4 gigatons as well. And how that shall come from direct air capture is a question that people can only answer me when I ask them. This can happen once we have nuclear fusion. We have fission already. With nuclear fusion we would have enough energy, but when comes nuclear fusion? It's also a big question. So the idea is to create a new building material that is by nature CO2 negative, which can scale up to the gigaton level. And then we will become CO2 negative and 2-degree, or hopefully 1.5-degree compliant. So our solution is called carbon fiber stone, or CFS. CFS is made from stone, and carbon fibers. And I have here a sample. It's a thin sliced stone. It's not melted or reconfigured or rebound with resin. It's a pure stone, and you can see that the stone is, once it's stabilized with carbon fibers, shows us its flexibility. So there is inherent flexibility within the crystal structure of these stones. Without that, the stones would be usable as building material. Because immediately you would experience hair cracks like in cement. That's horrible. We believe that this building material will survive many hundreds of years. We can also make structures like this. Typical structure from steel. It's a so-called I-beam. This I-beam is made from stone plates with carbon fiber layer inside two thin stone plates. And machining these plates that thin means that we derive a lot of stone dust as a waste. And if you would replace cement and steel on a global scale, we would cut around about 35% gigatons basalt and Gabbro stones annually, which would provide us with 20 gigatons of stone plates, replacing all concrete. And this would result in 15 gigatons of fine stone dust we could use for mass rock weathering. All the soils on this planet would be able to take up about 50 gigatons of fine stone dust every year. Our piece here is 2 times lighter than the same piece made of steel. It has the same load capacity and it's durable for hundreds of years. 1 kilogram of stone dust from Gabbro, that's what we measured in a 100 project by the German government, collects 450 grams of CO2. That is even almost 50% more than basalt. So the stone is really ideally suited for both, for building and for enhanced weathering. This could result into CO2 negative construction at global scale. I would say, we can even say now that CDR could become an initiator for a global carbon negative construction paradigm. Next slide. So the stone cutting will happen only with electrical energy. We don't need any fossil energy to cut the stone. The fiber reinforcement, we can also use basalt to help the carbon fiber to become less expensive. Glass and flux may be also a possibility. And bioresins binding the two together. The stone and the carbon fibers need to be connected somehow, and that we do with resin in the future with bioresin. We have made a life cycle test, like 10 million load cycles on a railway sleeper, which showed that the material is losing no performance or stiffness. Next slide, please. The climate impact. If we add 15 gigatons of stone dust, we could derive about 6 gigatons of CO2 annually. That would around about neutralize the cement emissions that we have today twice over. From hard to abate sector to a carbon sink or CDR. Even buildings become carbon negative machine. This is a house wall that was awarded this year in Paris at the JEC Award as a winner in the category of building and civil engineering. This wall is made from stone plates with carbon fiber reinforcement, and inside the 2 stone layers there is biochar as insulation material. So this house wall is as carbon negative as the same wall from cement would be carbon positive. Next slide. The market potential is really big. I don't need to go into much detail on this. the carbon credits for about 7 gigatons of CO2 that can be derived as a sink would mean a lot in addition, because the value in addition, because the cost of our building materials, once it's scaled, is at the same level than that of concrete and steel. Next slide. So, we can replace cement with a solution that is carbon negative, inherently carbon negative. It's the only solution that we can see at the moment that can scale into the gigaton levels. Next slide. We have shown durability tests, 10 million load samples, over 100 years stability. The weight is the same as aluminum. We can build 3 times lighter than with concrete and 2 times lighter with steel, using only 50% of the energy. That's another important point. Energy efficiency is often forgotten because the energy efficiency means cost. So our cost will eventually be even less than that of steel and cement. Next slide. We are producing already products. The flagship we are currently selling is a laser scanner for the steel making process, used to measure I-beams accuracy. In the middle you see an I-beam, the big guy. This is only a small showcase here for the cup. A real big I-beam that is made from stone and carbon fibers inside. And on the right hand side you see a landing platform for helicopters that we have built from thin CFS plates in a funded project from the German government to show that we can almost do any structures that are doable with other materials, even round structures, because we can bend the materials without any deficiencies or problems. And certainly for the buyers, we can also say that many products in the leisure industries could be made from carbon fiber stone. So everybody can buy a loudspeaker, for example, and can have our products which are carbon negative in their own form. Next slide. So we are currently planning phase 1 to scale our house wall up during the next 2 years. We are looking for investment for that. In phase 2, we plan an industrial scale up until 2035 into the 10 megaton arena with regional plants, and a global rollout until 2050 seems to be possible to really attack the cement and steel industry. The infrastructure is we need stone quarries. These stones, Gabbro stones, are available in really almost unlimited quantities on all continents, like India and Africa especially, but also in the US, in the northern region of Europe, and in Australia. Next slide. So the climate impact really would be turning the whole industry, the biggest industry on this planet, from a carbon positive cement emissions with 3 gigatons, an additional 3 gigatons from steel, could be eliminated and replaced by the carbon sink in the same order. That is big, this is real huge. And we could produce stone dust that comes for free out of our process. The stone dust will not cost because it's paid by the product. The energy to cut the stone slabs is in the equation of the techno-economic analysis, which is covered by the cost at the same level of today's building materials. So stone dust is a is a free gift, so to say. It needs to be dried and then spread. And it's not our job to do. We just are able then to deliver the material. Next slide. So the market potential, I don't need to mention, is very big. Next slide. And now we are seeking partners, like construction firms, quarries, architects, maybe even the cement industry may be interested to support us on an honest basis and not buy a small company and put it into the drawer. We are not going to allow that. Before this happens, we will give this as a free license to the developing countries that they could scale it up. We are already talking to China and Indian authorities to bring our ideas into the rest of the world very quickly. We also ask for donation because our financing is quite poor at the moment. We do owe everything from our own pockets. We have found a few angel investors which keep our operations healthy from time to time, and any donation could be found a link on our TechnoCarbon website. Join us if you want. You can spend €5 if you want, only once, or find people who can support us more. Next slide. There's no next slide. Here's the final one. Okay, so I think there may be many questions. There are not too many people here in the room, but maybe Chris, you can take this up now and ask me some questions, please.
Guys, thank you for that. Super interesting. Sounds very promising. What about waste and recycling? So presumably a building gets built with this material and at some point it gets torn down, maybe 20, 30, 50 years later. Is this material easily recyclable, and does it still then, is it still as compelling from a kind of a carbon perspective? Or does it just then, I mean, it's no longer, presumably once it's been installed in a building, it's no longer absorbing CO2. So if you're using it again, then presumably you're just using the material as second-hand material, not as a carbon sink again.
Yes, you're right. The material as it is here would absorb a little bit of CO2 on the surface. All the surfaces are stone. The carbon fibers are in the middle of the two stone plates. In each of these three plates of this only beam. Here we have the other situation where the carbon fiber is on the surface and the stone layer is in the middle. These measurement glasses that are shown for the steel industry are made of these materials because we have to bend them heavily, and that is why the carbon fiber is here on the surface. I mean, like this is not being bent like this, so we can utilize the stone on the surface. But if we want to break down an existing building, we can dismantle parts that prefabricated. Our house wall that I've shown you briefly on this picture is a prefabricated part. It could be dismantled completely as a whole part and reused as a whole part in another whole. And the cement industries are thinking about the same things, to reuse prefabricated building parts. If you really want to recycle this down to the single materials, it's also possible, because you can, with some instruments, peel the carbon fiber off the stone surface, and then have the intact, complete carbon fiber layer for reuse to be glued on another piece of stone that should be used in the future. So the recyclability is given, and we don't have to destroy everything. The most expensive part is the carbon fiber. If I can peel that off from the stone layer, then I can regain the most expensive part of this for second or third life. And the rest of the stone I could, for example, crush and use for enhanced rock weathering too.
Thanks, that's great. So at what stage in the timeline does the CO2 absorption happen? You get this stone from a quarry, you turn it into powder, and is it immediately then? So when does the CO2 absorption? When does the removal happen?
We are not doing the removal. We would provide a source for stone dust that could be used in agricultural soils that other companies who are fertilizing and selling to the farmers and helping them to spread the material through the existing mechanisms of capturing CO2 in soil. So we just would provide the base material from our production process.
Thanks. I think that was all the questions that immediately came to mind. But thank you for that presentation. Really interesting, and hope you find the donations and the investors and partners that you need to make this really large scale. It sounds super exciting. Thank you very much.
Thank you very much too, and greetings to all CDR enthusiasts.
Thanks very much. So that brings our session to a close. As many of you will know, this is the end of our 6th day at COP30 at the first ever Carbon Removals Pavilion, and we look forward to seeing many of you in person at the CDR networking event this evening on the banks of the river in the Botanical Gardens for a good time in the CDR community. Thanks very much, and see you soon.